conditions or under different conditions where the model of the system is changing as a consequence of those conditions. So with that said, I'll turn it over to Alex to walk through his work. Thank you.
Thanks so much, Nate. Yeah, hi everyone. I'm very happy to be here to defend my work on model learning for aggressive quadrotor flight. And thank you all for being here. So I want to start by showing the state of the art for what humans can achieve with quadrotors and just how exciting and aggressive these flights can be. This is an FPV pilot flying through a very narrow corridor, and you can see all aspects of the problem here are happening at very high speed: like planning, controls, perception. And this is something that one day we hope for autonomous algorithms to be able to do. And hopefully this thesis takes a very small step towards that goal. So in terms of what quadrotors are used for, there are recently so many applications have surfaced. And one of the reasons that we want to be able to fly quickly and aggressively is because of the limited compute on board. So the faster we can achieve the task and the faster that we can complete the objectives, we'll be able to do it with a lighter quadrotor with a smaller battery, for example. And for a lot of these applications, you may want to have precise and accurate controls. For example, here I've shown three. On the top left is a kind of a quadrotor that's omnidirectional, and it's contact mapping an archway. In the middle, we have an autonomous quadrotor exploring a cave in complete darkness. And on the right, we have an autonomous cinematographer. However, there are a lot of challenges that come up. One is we have nonlinear dynamics that increase in complexity as the speed and the acceleration of the trajectory you're following increases. We also have an uncertain environment and external disturbances that can be completely random and stochastic and time varying. And also, the faster we go, we suffer state estimation challenges. So not only does the control problem get harder, but the state estimation problem gets harder as well, and that also makes control more difficult. So the goal of this thesis is to enable accurate and aggressive flights in the presence of these challenges on model dynamics, external disturbances, and imperfect state estimation. So stepping back a little bit, we can define in general a control problem with two things: a dynamical system and a behavior specification. So a dynamical system takes in some input u, it follows the state x, and produces an output y. This is a very general formulation that many of you have probably seen. And many things can be modeled as dynamical systems, but like ecosystems in biology, chemical plants. But in this talk, we're only going to focus, we're mainly focusing on the quadrotor system. And as far as behavior specifications, this is just any way that you can basically prescribe a behavior for what you want the system to do. So some examples are like trajectories, goal states, reward functions in reinforcement learning, cost functions in optimal control. But in this work, we're going to focus on trajectories as our behavior specification. So the goal of a control problem is, given these two things, a dynamical system and a behavior specification, find the controls u that best satisfy the specification, whatever that may mean for the particular specification. So for our example, for a trajectory, we want the robot to follow the trajectory as accurately as possible. So on the top here, this is what typically happens. The robot will lag, it'll start oscillating. But what we'd like to see is minimal error. So something like on the bottom here, where the robot cleanly tracks the desired trajectory in the orange, with the orange dot. So there's this concept known as a forward model-based control. And the idea is very simple. If you can predict what the system will do, you can solve control very easily, at least conceptually. And you just say, I'm going to forward simulate a bunch of control inputs and pick the one that results in the best outcome. So we're given a dynamical system and some desired output y ref. And we essentially want to solve this optimization problem here on the right, which is find the controls u that minimize the error between the system output h of x and the reference output y ref. And we want to do this while following the system dynamics. So the ways to solve this forward model-based control range depending on the assumptions that you make. So here I've shown a spectrum of the different approaches. On the left, we have kind of the most explicit simulation approach, which is this broad category that may be called as model predictive control. And typically these methods require a lot of computes, but they're also very general. On the other side of the spectrum, we have more implicit simulations, such as dynamic inversion and differential flatness, which we'll be talking about in this talk. And these are, the advantage is that they require much less compute, but also they're more specialized. So they work in a smaller number of cases, and they make a lot more assumptions about the dynamics and about the cost functions that you're interested in. In the middle, I think a good intermediate example is something like LQR, which has a lot of different variants, but LQR, a lot of people may refer to it as MPC, but in its simplest case, it's just it makes simple assumptions such as a linear system with a quadratic cost and so on. So the point is that we can take a control problem and really reduce it to a simulation problem. And can we predict what's going to happen? And if we can, we just need to find the control inputs that give us the best outcome. So let's talk about what are the types of error that can come up in this type of model-based control. So I've split it here into two types. One is an inaccurate model, and this leads to bias. So these are things that are repeatable. So I mean, in a simple example, if you're shooting at a dartboard and you keep hitting the same spot, but it's not where you want to be, that is just an inaccuracy. And some examples of things are like drag, an extra payload, some structured miscalibration in the robot, like you have the mass wrong or you have the moments of inertia wrong, things like that. The second type is a stochastic model, and this is kind of results in variance in your output. So these are unpredictable things like if somebody pokes your robot randomly, or if there's turbulent wind, for example, a robot carrying a bucket of water, those types of disturbances are very unpredictable. And this leads to errors that are, I would say, more difficult to correct. And I should say that this is not a clear divide. I mean, there are some things that you may treat as biased that you may predict, but they're just too difficult. For example, you can run a fluid simulation to compute the way the water is going to affect the dynamics, but that's in practice usually way too difficult. The good thing about us and this thesis is that most of the errors that we see are actually due to bias, and a lot can be done simply by removing this bias. And we're going to leave the reducing the variance part to kind of different approaches and more engineering style approaches. So how can we deal with this error? So controls are a combination of feedback and feed forward. Here I've written a general equation that shows there's an error between some reference state xref and the actual state x. And we have this feed forward part, which is a function of only the reference. So really, what we want is to minimize the amount of feedback we need to use. So feedback is, by definition, a function of the error. So if you're using feedback, you've already screwed up. I mean, you already have error. So the goal is to be able to capture this error in the feed forward part so that the feedback has to do as little as possible. But in order to get accurate feed forward control, this requires an accurate model of the system. So again, the concept is if you can predict well, you can control well. And so what we're going to do is use model learning to correct this repeatable error or bias. And we're going to leave feedback to correct any of the non-repeatable error arising from stochasticity or things that you just don't expect. And that's also, we refer to it just as variance. And here's an example of some trajectory traces from a robot executing a trajectory. This is the position error. And you can see it's very structured, and there's kind of this repeatable error that we see. And after we apply model learning, we'd like to see something like this, where the mean of the error is reduced. And yes, you can still see some kind of oscillations, but it's noticeably better than without model learning. So quickly, I'm going to list the contributions of the thesis, and then we'll get into it. So we learn accurate models of acceleration dynamics, and we invert them using the differential flatness paradigm. We then apply the learned acceleration models to the feedback linearization controller. We also augment this feedback linearization controller to deal with control input delay, improving the robustness of that controller. Fourth, we learn and invert models on the angular acceleration of the robot. And finally, we perform outdoor flight experiments at high speed and high acceleration with imperfect state estimation to validate the approaches that I'm going to present. And really, the goal of this talk, here is the control equation. The general control equation is really on this second part. Here is the feed forward part. And this part does not depend on the state. It only depends on the reference. So that's what we're really focusing on. We're trying to get the most accurate feed forward controls possible. So first, I'm going to go into some background, going over the quadrotor modeling and how we can learn incremental models. And then I'm going to talk about inverting the learned models on the acceleration, feedback linearization next, and finally finish up with outdoor flight experiments. So first part of the background, I'm going to talk about the quadrotor model and differential flatness. So the quadrotor model, we model it as a rigid body with the constraint that the thrust is along the body's z-axis. So there are two forces that really go into the base model. There's gravity pointing down and just the thrust due to the rotors pointing in the direction of the robot's z-axis. The state space is the typical rigid body state space. There's position, velocity, orientation, and angular velocity. And the control is two things. One is the thrust along the z-axis, u, and the second is the angular acceleration about the body. And using this force diagram, we can derive the dynamics. So we can see that, the acceleration is the sum of the two forces. So it's the acceleration to the motors and gravity pointing down. And we have the angular acceleration, which just affects the angular velocity. And that's it for the base model. It's just a standard rigid body model with this additional constraint of the z-axis thrust. So the way I want to talk a little bit about the way control inputs are converted into motor commands. So if we start here on the left, I've introduced some notation where R sub I is the position of motor I relative to the center of the body, and F sub I is the force produced by that motor. So if we want to find out the torque that this particular motor is producing, we can just do R cross F, and we can sum up the torques from all the motors and get the total torque on the body of the robot. That's here. And we can just sum up the thrust to get the total thrust. And we can also represent this relationship as a linear mapping, which I've labeled here M. And finally, given that we have the torque and the thrust, we can convert that into accelerations just by inverting with the appropriate mass. So mass for thrust and moments of inertia for acceleration. That's the forward model. And as usual in controls, we apply the inverse model to get the right control input. So our controller is going to output. So it's going to give us a desired thrust and angular acceleration. And we're going to turn these into motor commands by reversing all of these steps. So we take angular acceleration, multiply it by inertia to get torque, and then we invert this linear mapping M to get the motor forces. So I want to take a moment to talk a little bit about differential flatness, because when you first hear about it, it may sound like this mysterious thing and this kind of weird concept, but I think it's very simple, at least in the way it's implied for the quadrotor. So differential flatness was introduced by Michel Fliess in 1992. He wrote a paper called On Differentially Flat Nonlinear Systems. And in this paper, he introduced this new class of systems called differentially flat. And really, this was kind of a different point of view. It was kind of taking the concept of feedback linearization and applying it from a slightly different angle to show how useful it can be. And the approach he took was from a very kind of high-level mathematics approach with differential geometry. But I want to take a moment to think about what is the simplest, interesting differentially flat system, and we can use this to kind of give us some intuition about how it works for the quadrotor. So if you think about a wheel rolling along a line, the wheel has some angular velocity, but it's also moving along the line with some velocity v. And because of the constraints that the wheel is not slipping, we can essentially derive this relationship between the velocity of the wheel and its angular velocity, and it's just multiplied by the radius. So what differential flatness allows us to do is express the quantities such as the angular velocity and the angular acceleration of the wheel as a function of its linear velocity and linear acceleration. So this is useful because if you want to, say, move the wheel with some linear acceleration, you can use these relationships to compute the desired angular acceleration and the torque you want to apply at the center of the wheel. This seems very simple, but it's not much different for the quadrotor, as we'll see. So how can we use differential flatness for trajectory tracking? So first, I want to start with overviewing the general trajectory tracking optimization problem. We're given some position reference Pref, and we want to minimize the difference between the actual position of the robot and the reference. That's this integral here. We want to do it following the dynamics. Well, we can also say there's an even harder problem, which is I want to be at the reference at all times. And this is strictly harder because, I mean, if this is true, the integral is 0, and this integral is always positive. So you can't do much better than that. You can't do better than that at all. So this is a harder problem. And the cool thing is differential flatness lets you solve this problem very easily. Essentially gives you the solution to this problem for free, because essentially the differential flatness says that given some trajectory Pref, as long as it is smooth, as long as you can differentiate that trajectory, you can compute the control inputs needed to follow that trajectory perfectly. And that's pretty amazing. So that's, if you recall the spectrum, that's all the way at the very kind of implicit simulation. It's kind of just using local trajectory at a specific point to compute all of the control inputs. And yeah, it's very efficient, but drawback is it does require smoothness up to a certain order. And for the quadrotor, that order is 4. It would require the trajectory to be smooth up to snap. So what does this mean for the quadrotor? Well, what this means is that we can convert a trajectory into control inputs. So given a position P and its derivatives, that's the trajectory, how do we compute the state control? So that is what differential flatness asks you to do. And again, the trajectory is position, velocity, acceleration, jerk, and snap. So that's position and its 4 derivatives. And the states of the quadrotor are position, velocity, orientation, angular velocity. And recall the control inputs are thrust upwards in the direction of the motors and angular acceleration. And so how we're going to do this is we're going to use the property that acceleration is constrained to the z-axis. And so essentially, if you want to accelerate in a certain direction, you just say, well, that's what my orientation needs to be. That's what my z-axis needs to be. And that's really it. And then to get the remaining control inputs, so to get angular velocity, you would just differentiate this, right? Because the angular velocity is the derivative of the z-axis. You may think of it that way. And we get this kind of interesting relationship where we have the orientation of the robot is constrained by the acceleration of the trajectory, the angular velocity is constrained by the jerk, and the angular acceleration is constrained by the snap. And so that's why you need the trajectory to be smooth. If the trajectory wasn't smooth, you wouldn't be able to get angular acceleration because you don't know what the snap is. So how this fits into the quadrotor control architecture is here in visual terms. So all the way on the left, we have the trajectory planner, and there are 5 outputs, but really you can think of it as conceptually just one output. You just get a trajectory, and this trajectory object can be differentiated to get the 4 derivatives. And if you, for a moment, ignore the green, which is the feedback, you can do the same thing without any of the feedback, and you'll still get a valid trajectory. And if the model is perfect, the robot is going to execute the trajectory perfectly. So essentially, all you need is the snap. You take the snap, you turn it into an angular acceleration, and then you get the right inputs, right? The rest of them are really just for feedback, right? You take the position velocity, and then you compare it to what actually is there in the robot, and you just adjust the acceleration to compensate. So this is a second order feedback controller. And the same thing happens on the orientation. There's a second order feedback controller that takes in, orientation position, which is orientation, and angular velocity, orientation velocity, which is angular velocity, and we get some adjustment to the angular acceleration. So the way this works in a little bit more math is, first, differential flatness provides these open loop feed-forward controls that are independent of the state. And I've represented this using this model, tau inverse, where tau is the forward model and tau inverse is the inverse model. And we add feedback to deal with non-repeatable disturbances and stochasticity or the variance. And these are the kind of the 2 controllers. Here is the first one is the PD position controller, and the bottom is the PD attitude controller. And the important thing to note is that there's feedback on all 4 components of the state: position, velocity, orientation, and angular velocity. And that's really it. And here I've highlighted the desired acceleration A in red, because that's what we're going to be focusing on in the first part. Is we're going to be improving that. I want to take a moment to talk a little bit about quadrotor attitude control, because there are some subtleties that are special for the quadrotor. So this is the typical form of the controller. Again, you have a position gain, so it multiplies the error between the desired orientation and the actual orientation, and same for the angular velocity. But one thing that's special about orientation is you can't just subtract it as the way you can angular velocity. So you need to come up with some metric that compares 2 orientations and tells you how do you get from the current orientation to where you want to go. And I've kind of represented this by this circle minus sign. So Euler angles, you should never use Euler angles. They're typically like the worst choice, but it's maybe what the simplest and what people think of, but it's actually ends up actually being more computationally expensive to use Euler angles than any of the others. So never use Euler angles. A common one is to use the shortest path in SO3 space. And that's probably what makes the most sense for rigid bodies. But since we have this additional constraint with the quadrotor that the acceleration lies at the z-axis, it's actually not the best for quadrotors, because it leads to these non-straight diagonal paths, as you'll see in a moment, and it couples the position and the yaw of the robot. What's better to use is just to align the z-axis. So ignore the x and y axes of the orientation, take the 2 z-axes and align them. And that does leave an extra degree of freedom, and that can be solved for by asking the question, well, where do you want the robot's x-axis to point, for example? And so what this looks like is on the top here is the SL3 error metric, and you can see the robot here is given a diagonal step. And the issue with the SL3 metric, which is the top one, is that it doesn't really follow a straight line path. Like if you see it, it's going to deviate off the path. And that's because of this coupling between position and yaw. Whereas the z-axis alignment method follows a much straighter path to the goal. And the reason for this is that the x and y axes don't matter for position. So if you want to focus on the accuracy and the straightness of your position control, you should really prioritize the z-axis. Another reason this fails, and I'm going to show this with a hardware experiment, is the position and yaw coupling. So on the left, we'll see the original SL3 control. And the robot is asked to go sideways and to turn 180. And what's really weird about this is that it ends up going down and forwards. So that's very counterintuitive, and you really wouldn't expect that. But that's what happens if you use this, this metric. Sorry about that. So on the right, you're going to see the z-axis control, and that's going to do a lot better. So because it doesn't couple the position and the yaw. So it's essentially what you expect. The robot goes sideways and just turns 180. So second part of the background is I want to talk about online model learning using incremental linear regression. So the beautiful thing about forward model learning with robots is that it's essentially self-supervised. You have a trajectory, you don't need to label any data, you can just discretize that trajectory and you have the data set right there. Essentially, the question is what's going to happen next? And you can set this up as a regression problem where you take the derivative of the trajectory and essentially predict it using the current state and input. And this is a direct setup where you're just learning the dynamics function f. And for our problem, for the quadrotor controls, we have some requirements or a method. And first is that we need to be nonlinear because the dynamics and disturbances are nonlinear. But we also need it to be smooth because of the differential flatness approach that we want to use. We also want fast incremental updates so we can learn things that happen online and we can adjust to the environment. We also want it to be stable and safe. So when the model doesn't have enough data, we don't want the robot to do something crazy. So here are some popular regression strategies that have been used for model learning in robotics. On the left, we have incremental nonlinear regression, and the obvious drawback to just linear regression is that it's not nonlinear. A common one is Gaussian processes, but the naive implementation of Gaussian processes are very slow, and the computation time actually scales with the number of data points. So as you get more data points, you end up doing more and more computation. And if you're running this online on a robot, eventually you won't be able to do it in real time. There's also something called a locally weighted projection regression, which does satisfy all three of the requirements. And this is a way to learn local models in different parts of the state space, and you can update them incrementally. And finally, we have incremental nonlinear regression, and that's simply just linear regression with some nonlinear features. And I'm going to talk about that because that's what we'll be using for the experiments in this thesis. And I should mention that sometimes you can actually make interesting relationships between Gaussian processes and incremental nonlinear regression, and we'll get to that. So given a data set of points that you want to fit a model to, let's say they're x and y, and you want to predict y, the minimization problem is just the error between the model's output y and the model's output w transpose x and the label y. And so here, since we're doing linear regression, I'm just going to assume the model is some linear function of x, and the parameters we're looking for are w. So what we do to solve this is we put all of our data points into a matrix x and y, and we just, this is standard linear least squares. This is the normal equations, and essentially this first part here is the pseudo inverse of the data matrix x, and you can this value w hat provides the solution to this minimization problem. However, what's typically a lot better to use is to do something called nonlinear regression, where we project the input data into a high dimensional feature space or some nonlinear feature space. So for example, for polynomial regression, we take the input x, multiply some powers of it, and that's how you do polynomial regression. There's also an additional important aspect, which is called Tikhonov regularization or ridge regression, which is this term here. Essentially, this adds a 0 prior on the learned weights W. And this is helpful because we can make the model sane when it doesn't have enough input points. A particular feature that's very powerful for this approach is something called random Fourier features. This is where you take just random frequencies and project your data into this kind of Fourier space. And that turns out to be a very, very good way to do nonlinear regression for smooth functions. And that is how essentially there's an interesting connection between that and a Gaussian process. The other interesting thing to note is that these matrices here that we use to compute W, it's also true for the nonlinear case, they actually don't get bigger as the number of data points increases. So yes, the matrix X gets a new row every time you get a new data point, but the quantity X transpose X is really only, its size is only dependent on the dimension of the input N. So that's really cool. And what you can actually do is update this value recursively. And you don't need to, you actually can do it in computation. It doesn't scale as the number of data points goes up. So that's very good for online model learning because computation time stays the same no matter how many data points you have. So now I want to move on to the first part of our work, which is how do we learn acceleration models and how do we invert them for control. So if you recall, the original Quadrotor model has two forces, gravity and thrust. And the obvious thing to do is, well, let's just consider all the other forces. And I've labeled that in red here, A sub r. And we're going to attempt to learn all of the other forces with model learning. And what we can do is we can compare what actually happened to the robot, so the actual acceleration, and what we thought happened using our prior model, which is the sum of these two forces. And we just want to predict that difference. And that's going to be our acceleration model. The important thing here is that we're using the prior model as a starting point because this prior model actually does quite well when you're flying at low speeds. So you want to kind of build on it and not lose anything by doing model learning. So once we've learned this model, let's talk about how we can use differential flatness to generate the control inputs. So if you recall before, we were able to compute the z-axis from the desired acceleration and the control input u from the desired acceleration. But if we make our model super general and have it depend on the entire state input, this is actually not possible to do analytically because you have a u here and you have a u here. And you can't solve for u without knowing some form for the model. What we can do is we can actually reduce the dependencies on our model. So the simplest one is we can say, well, we're just going to use position and velocity. So if our model only depends on position and velocity, we can solve for u because this term does not depend on u. And an important point here is that if we want to compute the other control inputs, so the angular velocity and the angular acceleration, is we need to differentiate the model. So it's not enough just to sample the model at the point you are now. You need to also sample its derivative. In a way, by sampling this derivative, you're kind of predicting what's going to happen to the disturbance locally for a short bit of time. There's a slightly more complicated setup, which we can actually include u here into the acceleration error, but we need numerical optimization. So because this is a nonlinear model, you can't solve for uz analytically. We run a numerical optimization routine that actually ends up being fast enough to solve online. And this allows us to compensate for disturbances that depend on the input, which I think is really cool. And again, to compute the other control inputs, we can just differentiate that and we get the angular velocity, which is needed for feedback, and the angular acceleration. So really, these derivatives predict what's going to happen through to the disturbance. If you don't look at the derivatives of the model, you don't really know what's going to happen to the disturbance in the future. So a few comparisons to related works. There have been a lot of works that consider drag into the model, but they don't consider a nonlinear term like we do. So first is differential flatness has been extended to work with linear drag terms, and that's work from Scaramuzza's lab. And this is very efficient. but it has some drawbacks. It's not nonlinear, and it cannot deal with constraints, and it also cannot deal with input-dependent disturbances, like disturbances that are a function of UZ, as we saw. There are also works that use Gaussian process models, but like I mentioned earlier, those typically have to be learned offline, and they're not very efficient. Whereas our work, it's efficient, and it can also deal with nonlinear disturbances. And it can also deal with input-dependent disturbances. The drawback of our work, however, is that it cannot deal with constraints because of the smoothness assumption. So if you have any type of constraint on actuators or hard state constraints, that's or even disturbances that change discontinuously, that can't be predicted by our model, because by looking at derivatives, you can't predict the discontinuity. So we evaluate this method on this hardware quadrotor. It's a very light and agile quadrotor. It weighs about 0.5 kilogram. It's got 7-inch props, which are like pretty large relative to the size of the body, as you can see here. And we use Vicon for motion capture for this first part of the experiments. And I want to show you this vehicle and how fast it is. I mean, so here the vehicle is traveling about 4 meters, and it goes up to 8 meters per second in 20 meters per second squared acceleration. I think that's pretty insane. It's pretty scary because if it goes in the wrong direction, it can hit you and things like that. But yeah, so the point is to capture the capabilities of this vehicle and to do interesting things with it. So for the hardware evaluation, in order to simulate or sort of emulate some disturbances, what we do is we put a large piece of cardboard on the robot. And so you can see the cardboard is basically as large as the robot. And what this is going to do is accentuate any kind of wind and drag disturbance. So 3 experiments, we're going to turn on the fans, and as the fans hit the cardboard, the robot is going to spin in place. The second experiment is going to do a 3-dimensional trajectory flying with this cardboard. And finally, the third experiment is same trajectory, but with fans on top of that. And 2 questions we want to answer is, first, how well can we predict the accelerations that the robot is feeling? And second, using that prediction of the acceleration disturbance, how much can we reduce the tracking error? So the first experiment is basically the goal is to stay still, station keeping at a particular point while spinning in place with the fan hitting the cardboard. And as a baseline, we're going to compare to an adaptive control method, which estimates the disturbance recursively, but it does not model the disturbance. So first, I'm going to show you what the adaptive method looks like for this experiment. So the vehicle is going to start from the right, and it's going to come in. You can see the fans are blowing from the left, and the fans are pushing the cardboard so that the vehicle has to stay at an angle to stay in place. And as it starts spinning, you can see the disturbance is changing so much that the vehicle is oscillating back and forth. So that's not great. We want it to stay still in one place. So now I'm going to show the model learning, and I've showed the beginning again because I want you to see how it learns. It doesn't have any prior data, and it's first encountering this disturbance for the first time. So the first spin is similar to the adaptive method. It's quite oscillatory, but after a few spins through, it starts to stay in place a lot better than the adaptive method. Already you can see kind of it's basically anticipating the disturbance and changing the angle of the robot to account for the fans blowing on the cardboard. So to summarize the results here, on the top left, I've shown kind of both of the videos overlaid. And in the background, the lighter one, you can see the adaptive method, and you can see it's moving a lot more. And if we look at the position data, we actually see around a 50% position improvement relative to the baseline method, and a similar improvement in the speed. On the top right, I've shown kind of an animation of what we actually learned. So the blue data points are the raw disturbances, and the orange is what the model predicted, and they're spread out over a yaw. So as the yaw of the robot changes, the disturbance changes. You can see it gets lower at certain points and higher at certain points. And we can see that our learned model in orange has captured the mean of this disturbance really well. So we can essentially compensate for it without any of the noise coming from the blue data points. So we should ask, why does the adaptive method do so poorly? And the answer is that it doesn't have enough time to really get the right disturbance. You can see here in orange is the adaptive method, and the green is our prediction. And essentially there's this phase offset because it's just lagging. The reason is that the adaptive method has to somehow deal with the noise, and in order to deal with that noise, it has to kind of delay its output, and that leads to a lag, and that leads to poor performance. The modeling method has the advantage that it can assign particular points to a certain point in the state space and then average them. Whereas the adaptive method can't do that. It can only say, this is what happened now, and I can't map it to the state. The second experiment is we are flying with the cardboard in the three-dimensional trajectory. This I'm going to show you what looks like just for the baseline method, just so you get a sense of the trajectory. So it's both spinning and moving in these weave pattern to kind of change the disturbance as it's moving along. What we see when we learn a model on this data is that, again, our prediction in orange tracks the mean of the data points quite well, whereas in green is the adaptive method and it lags just as before. However, when we actually apply this model, we don't get an improvement in tracking error. Essentially, the error is roughly the same. Okay, there's a slight improvement in the speed, but the position tracking performance is very similar. And after looking at this, I realized it's because we run into motor saturation, and this really highlights a drawback to our method is that it can't deal with these constraints. So unfortunately, we didn't do as well here at this experiment as we would have hoped. The third experiment is the same thing, but with the fans. So the fans are blowing on the vehicle as it's carrying the cardboard. This is the adaptive method. And I'm going to play this for a few seconds, and you can see that as the vehicle encounters the fans, the wind from the fans is going to deviate off path. Now, the same thing with model learning is as it's flying, you can kind of see it anticipate the wind from the fans and change the angle accordingly. So again, the results show a pretty significant performance improvement. We've improved position performance using model learning by around 44%. And just to show the convergence of the model, here's an error plot per the iteration of the trajectory. And after 2 iterations, we've already converged to the lowest error of 14 centimeters. This is an animated version of the model that's learned. So iteration 1 is this one here. And you can see it's not quite matching the blue, but after iteration 2, each iteration consistently tracks the blue data points quite well. Now I want to move on to our second part, which is talking about the feedback linearization controller and how we can robustify it. So feedback linearization is a theoretically appealing controller, but it's in practice very, very brittle. And we want to address this in 2 ways. The first is to compensate for thrust input delays. And the second is to use our acceleration error model from before to improve the model that feedback linearization uses to give us the linearized system. And a goal for this section is, can we make the feedback linearization comparable to the cascaded method on a hardware system? So is it feasible to use for aggressive trajectories? I want to talk a little bit about the differences between the traditional cascaded controller and the feedback linearization controller that we're going to use. First, starting with this flat transformation. So recall, we have this transformation that we can call tau, which takes states of the robot and controls of the robot and converts them into flat states. So position, velocity, acceleration, jerk, and snap. And we can do this just using the dynamics. We can just find the acceleration, differentiate it to find the jerk, and so on. And what the cascaded controller does is it inverts this model using the differential flatness, and it generates some state references, and it generates the control inputs. So I've represented this using this tau inverse. But what's important to note here is that the feedback part happens on X. It happens on the state of the robot, and that's a nonlinear space. Feedback linearization has the feedback in the linear part of the space. So first we take the state, we map it to the flat output space, which is linear, and we do feedback on the flat space. And the advantage is that with this, the assumptions of a linear controller typically hold much more. So a lot of the second order controllers, they're designed with linear systems in mind. And they kind of, the assumptions hold much more in this flat space. And to get control inputs using feedback linearization, you get your feedback output and map it right through using the inverse. So it still uses the inverse mapping, but first it also, uses the forward mapping to convert the state into the flat space. So why might we want to use feedback linearization? Well, first, a linearizing error response can be seen as optimal or good. So here I've shown kind of a robot given successive step inputs sideways with no change in altitude, and feedback linearization is on the bottom. And because of the linearizing error response, you can see that feedback linearization actually deviates in altitude or in Z a lot less than cascaded. So the cascaded one is going up and down, and feedback linearization is staying relatively at the same level. Another reason is kind of an obscure one, but it's easier to apply iterative learning control to feedback linearization. And I'm going to show an example of this. First, I'm going to show you what the experiment looks like. So in this experiment, the robot is carrying a really heavy pipe. And the robot doesn't know about this pipe. It's actually quite large and heavy. And it's asked to just translate it along a trajectory. And you can see this is the first iteration before any control improvements. And you can see it's not quite getting there at the required speed. It's a little bit slow, and you'll see what I mean when I compare it to the next one. But we can use iterative learning control to essentially repeat this trajectory over and over again to see how well we can do at the very end. And this is the results. So you can see that it moves a lot quicker. And the interesting thing is that we can actually only successfully do this with feedback linearization. If we try to attempt this with the cascaded approach or the PD approach, we actually don't converge to the right trajectory using iterative learning control. Now, there may be formulations of cascaded control that with particular change in the iterative learning control that let you do this, but at least applying these two controllers, feedback linearization is the only one that converged to the right trajectory when we do iterative learning control. So how do we apply feedback linearization to Quadrotor? Well, we need to use this thing called dynamic extension. And the reason is that implementing this forward mapping here to get, for example, the jerk, so to get the jerk, we just differentiate the acceleration. It requires knowing u dot, but we're choosing u as the control. So we can't compute the jerk if we're choosing u because we don't have u dot. We don't know what the derivative of our control input is. And similarly for snap, we can't get the snap because it needs u double dot. And you can numerically differentiate the u output, but that's not right. And since the u depends on the state, it ends up not working very well. So the solution is something called dynamic extension, and it's essentially you delay your input u. So you put the u into the state, and you put u dot into the state, and then you actually are picking u double dot. And now you have u dot because it's in the state. And so but the disadvantage is that now we have to, in order to apply this to the real system, which takes u as input, we need to doubly numerically integrate u double dot, and that can lead to issues. So double integration of u double dot makes motor delay much worse than it already is, and it leads to these oscillations in altitude. So the solution we apply is to model the thrust delay using this first order delay model. So we're saying the derivative of the thrust is going to be some, so it's just an exponential convergence to the actual thrust. And this is just a simple delay. The beautiful thing about this is that applying this model with dynamic extension allows us to only integrate once. And that's nice. So we kind of hit two birds with one stone. We're modeling the delay, but we're also helping our case by not having to double integrate. And now we only have to single integrate. And the details for this are in the thesis. So I'm not going to go into it, but it does improve the performance when executing step trajectories, as we saw on the hardware. So here I've shown traces from 4 different types of feedback linearization configurations. In the blue is the one without any delay modeling. And you can see because of this double integration of u double dot, it oscillates quite a bit. But if we vary this delay constant, we can see that, for example, a delay of 5 and 10, keeps the altitude a little bit more steady. So this thrust delay modeling kind of improves the Z response. And to answer our earlier question, can we make feedback linearization viable? Can we make it comparable to PD? The answer is yes. And we get similar error when using feedback linearization than when using PD. And that makes sense considering what we talked about in the beginning of the presentation, because this error really is a function of the accuracy of your feed-forward model and not the particular feedback that you're using. So finally, I want to talk about some outdoor flight experiments that we did to validate the approaches that we just talked about. So the goals for flying outdoors are to go fast, right? Because the faster you go, the more disturbances you feel from the wind. And we want to hit speeds at least 10 meters per second. With flying outside, though, come some challenges like wind gusts that are very non-repeatable, and they show up as acceleration disturbances that are stochastic and time varying. And we also, since we're not inside anymore, we don't have the beauty of motion capture. We lack a state estimate that's both accurate, precise, and high rate. And some results we want to focus on are two things, as usual: minimize trajectory prediction error, and second, using the improved prediction, how can we minimize trajectory tracking error, and how well do we do over the baseline adaptive method? And we conducted these experiments in a large open field shown here. We went to this abandoned US Steel waste dump, but it's actually quite nice. It's a grassy field, and it's nice because if you crash on the grass, it's not as bad as crashing on concrete or something. The vehicle that we use is essentially the vehicle from before with an added state estimation and compute payload. So it's a custom-built quadrotor. It has a thrust-to-weight ratio around 4, and we've included a Intel RealSense T265 for vision-based state estimation and a GPS module on top shown here. For compute, we use NVIDIA Tegra TX2, and all of the model learning and control is implemented on that computer. So a little bit about the setup. So we're using acceleration model learning, as I presented earlier, with incremental nonlinear regression with 50 of the random Fourier features. And for this experiment, our input features are velocity. And the idea is that the faster you go, the more drag you'll feel, and that disturbance due to drag is going to change as a function of the velocity. This model learning happens at 100 hertz if we're using the vision-based state estimate from the T265, or 5 hertz, which is quite low if we're using GPS. And also, we are using an angular acceleration disturbance component that I didn't talk about in this presentation, but you can read about more in the thesis. And this is running at 2 kilohertz on the embedded firmware. And we implement this as an asymptotic common filter that estimates the angular disturbance. So to summarize what's happening in the dynamics, we've added these 2 extra components here: a correction to the acceleration, A sub air, and a correction to the angular acceleration, alpha sub air. And this linear acceleration is, as before, it's computed recursively using this incremental nonlinear regression equation. And the output of this is just a linear function of these parameters W. And phi here are the 50 random Fourier features. So we take x, which is velocity, we multiply by all these random frequencies, take sines and cosines, and then linear function of that. So the trajectories we're going to run are 9th order minimum snap trajectories that are figure 8s. And I've plotted the position here on the top right and their higher order derivatives on the right here. And we have 4 different experiments and 4 trajectories, first starting with 8 meters per second, then 12 meters per second with a span of 40 meters, and finally 14 meters per second and 17 meters per second. And the faster we go, the higher the acceleration, because we need to hit those velocities. So at the very end, we're hitting highway speeds, close to highway speeds at 61 kilometers per hour and 1.2 G's acceleration. That's not including the acceleration that we need to fight gravity, which is 9.8 pointing up. So okay, here's the first experiment. And for this experiment, we use T265 for vision-based control. And this is a 20-meter trajectory that's going at 8 meters per second. So this is the robot taken from far away view, and you can see it's executing the trajectory. This is just to give you a sense of what it looks like. And for this, when we apply model learning, we actually improve the performance by a lot. And the baseline adaptive method gets 33 centimeters per second speed error, and our method gets 13. And so you can see here in the plot that our method in orange achieves the desired speed a lot better than the baseline method. And to give you a sense of what it learned, here's again the acceleration output. In blue are the raw data points, and in orange is our prediction. In red, I've shown the first prediction, and because of the incremental online nature of the model learning, the first prediction isn't quite as good, and it's a little bit oscillatory. So, yeah, but after the first iteration, all of the others look quite good, and the orange matches the mean or the bias of this acceleration disturbance quite well. So unfortunately, when we tried the faster experiments with the vision-based state estimation, there were some failures. So unfortunately, the T265 actually can fail quite catastrophically. So here's an example of this. The robot is circled in white and is executing attempting to execute a figure 8, but then there's this massive drift upwards. And unfortunately, at this point, we had to kill the robot, and it ended up plummeting down and crashed into the grass, thankfully. But this is not good, and it really presented a difficulty to running these experiments. So what about air pressure? Can we get a better Z estimate of this so we can avoid what happened in the previous video using the barometer? And so the answer is, yeah, maybe, but but it's complicated. Here's a plot of GPS Z and barometer Z. And you can see like here the robot is taking off and that looks really good and fine. But then as soon as we start executing trajectories, we get these spikes in the pressure. And so it interacts really well with the speed of the trajectory, the speed of the robot. So you can say, well, okay, I can learn a model, like how does the barometer output change as a function of speed? But then you're kind of saying like the barometer output depends on the state estimate, and it can quickly get very complicated. And so in theory, yes, you can like run a giant optimization to put every sensor you have into some giant filter. But sometimes in practice, if one of these modalities fails, it ends up ruining the entire thing, and because of some failed assumption, and you end up regretting putting it into the optimization. So for the next experiments, we just decided to stick with GPS as our state estimate, and we have to deal with the issues that arise with running control at 5 Hertz and running model learning at 5 Hertz. So with GPS control, we continue. Here's the trajectory at 12 meters per second. So this one's a little bit faster. It's also a bit longer. It's 40 meters instead of 20 meters. So that's the trajectory. You can see it's quite large. And again, our model learning method, it does improve the performance. We go from error 51 to 28 centimeters per second. And we do achieve this desired speeds of close to 12 meters per second, whereas the baseline method falls short at around 11. And then third experiment is 14 meters per second. So we're increasing the speed yet again. And the same thing, GPS control. And here you can see the robot. This is the fastest portion of the trajectory, speeding across. And we run this, of course, with both baseline and model learning. And again, we reduce the error. So it goes from 57 centimeters per second to 38. But you'll see that here in this first trajectory, we have 93 centimeters per second. And this number is, not including this one. So the rest are all good. But what happened during this one? Well, let's see here. So I guess first I want to point out that the clouds are actually moving very fast here. So it's quite a windy day. So we had a lot of, these non-repeatable disturbances. This is the first iteration with model learning. And you can see that the robot is a bit unstable. It does finish the trajectory, but it kind of deviates and ends up bobbing up and down. And so if we look at the second iteration, after collecting that data, this is the same model, it's continuing to learn, but this is iteration 2. You can see that it's a lot smoother. And so what likely happened is that during that first iteration, either there was a wind gust or simply the model didn't have enough data points, and it resulted in this kind of slightly suboptimal output. So that's something to look out for when you're applying online model learning incrementally. And finally, we have the 17 meter per second trajectory. So this is a robot. It's going pretty fast. And you can see some drift there at the end, because this is with the GPS. The GPS altitude actually drifts a little bit as well. But unfortunately, for this flight, we don't have enough data to conclusively say that we reduced the error. We're only able to run one of the model learning. But I do believe that given more data and more trials, we're able to reduce the error here as well. So to summarize the outdoor flight experiments, we want to ask first, what acceleration disturbances were felt by the robot and how well did we learn them? So here's all of the trajectories we've ran and their disturbances. So you can see in the blue, which is the slowest trajectory at 8 meters per second, disturbances are, they're still high. I mean, it's 2 meters per second squared, but it's low compared to the others. So at 12, we go up a little bit, at 14 in the green, and then at 17, we get disturbances reaching basically 1 G of disturbance, which is pretty insane. And so how does this look like after we correct for it using our learned models? Well, with a linear model, we get something like this, where maybe the blue is fully compensated in the orange, but say the red still has some disturbance there. When we apply a nonlinear model, which is what we use, incremental sparse spectrum Gaussian process regression, or SSGPR, we get a much better picture, right? So the means of these disturbances seem to be captured better than the linear model. And if we want to see this in the aggregate, we can see this here. So this is essentially the same thing as before, but in an aggregate versus over trajectory speed. The first thing I think that's interesting and kind of obvious is that the trajectory speed affects the strength of the disturbance. So the faster you go, the more disturbance you feel. For example, at 8 meters per second, we have an average trajectory disturbance of around a little bit less than 1, but over at 17, we have up to 2.5. And this is the average along the trajectory. So there are peaks during the trajectory where this disturbance is a lot higher. The second thing is that both our model learning methods have successfully improved the trajectory prediction error. We've reduced this disturbance by at least half in both cases. But also what's interesting is that the nonlinearity of this disturbance scales with the speed. And so really the benefit of doing nonlinear model learning is high when you're moving fast. So basically at 8 meters per second, at 12 and 14 even, the nonlinear method does better, but it's really close to the linear method. At 17, we really need the full nonlinear method to capture a lot of this disturbance. And finally, summarizing the error plots. So here I've shown the mean errors in orange, in the big dots, and each individual trajectory has tiny dots. And we can see that we were able to successfully reduce the error, with 5 Hz state feedback at 12 and 14. And at 17, of course, we were not able to. But another thing to note here is that the variance is gone up. So yes, we've reduced the total error by reducing the bias, but due to the incremental nature of our model learning, we've increased the variance of the system. And you might ask, is that a good thing? Maybe you prefer a repeatable robot or a robot that does what you expect. And so you can notice that the baseline system is actually quite repeatable. Each time you run the trajectory, you get the same error, even at say 17 meters per second. But yeah, so the takeaway in terms of the thesis is that yes, we're able to successfully reduce the tracking error at 8, 12, and 14 meters per second. So to recap our objectives, which is we wanted to do accurate aggressive flight with unmodeled dynamics, external disturbances, and imperfect state estimation. So first, we've done over 1,000 flights, which I've only realized this because I keep all my flights in a Google spreadsheet. And when you get to 1,000, you have to add another 1,000, which I thought was weird. It's not infinite. And so I had to do this twice. So we've also inverted learned acceleration models. So that kind of satisfies 3 of those checkboxes. We've done the same thing for robustifying feedback linearization. We've also learned attitude dynamics because fortunately, due to time, I couldn't show this here, but it's in the thesis. And finally, we've evaluated all of this outdoors with imperfect state estimation. There's so much that this didn't explore, so many things that could have gone better. But I just want to highlight a few future works that I think are sort of related here. So the nonlinear optimization that I talked about for input-dependent disturbances, that should be explored more in outdoor settings, as well as for learning models, like what actually is the benefit of that? Because so far, we've only really evaluated that in simulation. Second, we consider 2 different feedback strategies. We consider the cascaded approach and the feedback linearization. And we know from experience that the cascaded is more robust. But how, can we quantify that? Why is it more robust, and how does the accuracy of the model affect what feedback strategy you should use? I think as we deploy more learned models into the practice on robots, it becomes more important to be able to, for sure, say, this is the best feedback strategy I can be using, given this model and given this operating condition, for example. And finally, I think the models I've learned here have been, relatively low data. I learned models from maybe 3-4 flights at maximum. But I think for the future, we really need to do large-scale meta learning of adaptive methods that are simulation-driven. And I'm really excited about that. So yeah, thank you everyone for coming to the talk. And I'd like to thank the committee, the lab, and especially Janae and Eve for helping me do my field experiments. That was tremendously helpful. And I'd also like to thank the 4 robots here. They've all contributed tremendously, especially this last one who crashed a lot. So thank you.
Great, thank you, Alex. I'll clap on behalf of everybody.
Thank you.
Great job. Yes. All right, we'll now move to questions. We'll start with the committee. Then after we have a chance to talk to the committee, we'll open up to the audience. And then we'll check back in one more time with the committee and the audience if there are any further questions. So with that, let's start with the committee. And we generally start with the external committee members. So that's Giuseppe. So Giuseppe, do you have any questions for Alex?
So first of all, very nice work. I really enjoyed it. I mean, my first question is more, I mean, nothing really substantial. I was mostly just curiosity. I mean, you mentioned that there are many approaches that you mentioned for, learning these kind of models and so on. And you learn directly, I mean, without, for example, you don't incorporate the linear drag or other things. Do you think that this can be, I don't know, beneficial and your learning approach would still work the same? Or do you need to modify anything in that case?
Yeah, I think if you have a better prior model, certainly it's better. If you have drag parameters, let's say linear drag parameters that are really accurate and you use them, you'll be starting at a better point. And so then your model would say only be learning the second order dynamics. Another really easy win that I didn't talk about is running both the adaptive method and the model learning method. So that would be an interesting way to deal with both the time varying kind of faster changing stuff and the model learning. So there's no reason why the adaptive method can't use the learned model to learn its a faster changing disturbance on top of it. So you have a slow changing part, which is the model, and then the fast changing part, which is the adaptive. So yeah, I think that, I mean, in practice, if you were to implement this in a robot, absolutely, you should throw everything you have at it. Like the better model, the better it is. So I don't think in terms of the learning, you'd have to change too much. As long as every model you use should agree. You should use the same model in all of the modules.
Okay. Then the second question is, in the outdoor experiment, you used basically the feedback linearization, right? In terms of controller, or you use what kind of control, or do you compare with the different strategies?
Outside, we used a cascaded controller. We didn't run the feedback linearization controller outside, but I don't think there's any reason why it wouldn't work. So the issue with feedback linearization is if you have high error, there's an issue with that integration where you end up oscillating, and also there's a pretty bad singularity if you end up upside down. I think there are solutions to that, but just for safety, I felt safer using the cascaded approach outside.
Okay, I see. No, I was a little bit confused on that. Okay. So you just use the cascade with basically with the compensation of the first part that you talked about.
Yes, we have compensation for linear acceleration, and also we have this adaptive filter on the attitude.
Yeah, yeah, that's very interesting. Okay, for now it's enough. Then I can ask more later. I mean, I'll leave the stage for other people.
Great, thank you, Giuseppe. Chenglu, do you have any questions for Alex?
Yes, yeah, I just want to understand the difference between this method and ILC in a high level. I can see a lot of differences. For example, this method builds a model and it maps the states to the noise, the A error. And then this can actually essentially does not require us to do the learning in a fixed trajectory if the trajectory deviates a bit. And is there any other differences between this method and ILC?
Yeah, so ILC, I think of it as a kind of an inverse control method, right? ILC directly updates the control inputs. So for example, for that pipe, when we're carrying the pipe, at every point along that trajectory, we're computing angular accelerations and thrusts that should be updated. And so like you said, you can't use that in other trajectories. So, I mean, that I think is the absolute biggest difference. Whereas if you learn the model, there's an acceleration term that's used, and that acceleration can be used to predict what's going to happen in future trajectories. You can't really use the ILC output, at least the way it's naively implemented, for anything else, really. I mean, even if you change the trajectory slightly, maybe you can seed it with the old input corrections, but it's really limited to that one trajectory. But of course, the advantage of ILC is that you get a more certain guarantee that you will reduce the error because you're directly optimizing for the error. ILC looks at the error and says, what do I need to do to lower that error? And it computes that correction. But forward model learning, which is I'm doing, indirectly minimizes the error by minimizing prediction error. So I think there's some interesting theorem you can say, well, like if my control is implemented correctly, then minimizing prediction error is the same as minimizing tracking error. But in practice, there's certain cases where like that doesn't end up happening.
I see. And actually, ILC, in order to make it converge, you need to have a bound on the error that you have. So it's also kind of the model, although you don't have an accurate prediction on how big the error can be, but you need to bound it in order for your ILC to converge. Maybe. Oh yes, go ahead.
Yeah, I think so. For the trajectories I ran it, I don't think I applied an explicit bound for the error. because so that first trajectory with the pipe, that was kind of like the maximal error that we saw, and every iteration of ILC kind of reduced the error. And yes, there are a lot of things that you need to do to get it to work, like you need to regularize the corrections. You need to, if you output something crazy, you don't want to send that to the robot and stuff like that.
Cool, great. And then my second question is, since you mentioned you're using random Fourier features for your regression, where does the nonlinearity come in?
So the nonlinearity is essentially like if you project your data to Fourier space, for example, you can kind of reconstruct any smooth function. So because sines and cosines are nonlinear, a linear model on top of the nonlinear features effectively is nonlinear.
I see. I was treating Fourier transformation as linear mapping, but it's only linear in the frequency space, and then you're actually doing everything in a time domain.
Yes.
So then sine cosine becomes nonlinear functions. I see.
Mm-hmm.
Cool. Yeah, I have several other questions, but I can wait till the end. Those are very detailed questions.
Okay.
Great, thank you, Cheng. And Chris, do you have any questions for Alex? Chris, I do not hear you. Does anyone hear Chris?
No.
Oh, I see Chris.
We see you. We do not hear you. Let's give him a few more seconds and then we'll go to the audience and come back to Chris. Give him a chance to check his mic. Yeah, getting the thumbs up from Chris. Let's go to the broader audience. Does anyone from the audience have a question for Alex?
Right, I have a question. All right, Alex, great talk.
Thank you.
So I wanted to follow up on what Chang Liu mentioned, which is you said that ILC is only useful in scenarios where you're trying to track the same trajectory again. So any sort of corrections, feed-forward corrections that you learn are useful only for that trajectory and does not really generalize across trajectories. But you could always parameterize the feed-forward correction that you're making of what trajectory you're tracking, and then learn the correction so that now you can use this feed-forward correction for you try it.
Anu, I think the last part of your question cut out, or I didn't catch it, but if what I caught is that you want to not learn the actual control inputs, but learn something else in ILC that you can then reuse for other trajectories, is that right?
Yes.
Yeah, that's a great question, great point. Yeah, absolutely. So in principle, you can optimize anything. You can say the goal is to optimize tracking error. You can pick anything as your parameters, right? You can pick a model as your parameters. And that would be an interesting way to do forward model learning that's maybe more guaranteed to reduce the error. And yes, maybe something in between, like you suggested, is you can use the trajectory, kind of abstract that away and kind of put some other parameters that can be reused. And there are some works that do that. So I think it's actually not that explored. I think the question of how do you best learn models, a lot of people just assume, well, just optimize for prediction error, which I did in this talk. But certainly, like you said, you can change the parameters in ILC to be something else that can be more generalizable. I think that's, yeah, it's great direction.
All right.
Great. I see that Chris joined by a second instance. Chris, do you have audio?
Okay.
Yes, we have you.
Sorry about that. Zoom is very unreliable. Okay, so my first question is robustness. There are a lot of people who believe you only get robustness if you view things from a frequency domain approach, and you somehow do H infinity or something to keep the high gains under control. And that's especially true with these rotorcraft where you have many more dimensions in the state that that you don't model in your state space representation. So how do you get frequency domain robustness approaches into these learning approaches?
So I guess a direct answer may be that since we're using frequency features anyway, we can just say we're not going to use any high frequency features, and then we can guarantee that the frequency components of the model's output, given the frequency of the state, is going to be at most this, and then you can say like, okay, I'm not going to have issues with high frequency stuff. So that's like an easy answer. You can always just like weaken your model, but then you're losing some of the bias correction. So it's always like how much do you want to correct the bias? How much can you constrain the variance? So it's like a big challenge. But in terms of like you saw in that flight with 14 meters per second, like even with the supposedly safe parameters I was using, it was kind of destabilizing the vehicle of this model. And so it's important to kind of address that a little bit more rigorously, I think.
Okay. In the learning world these days, everybody takes whatever state space they start with and they embed it in some latent space.
Mm.
Why aren't you embedding things in some latent space?
I think for this type of learning I'm doing, it was doing okay. Like I could learn the mean of the model well with just the features. I mean, I guess I am. So my latent space is the features, the frequencies, right? So random Fourier features, that's my latent space. But you can imagine there must be a better space. And I think absolutely, if you want to do kind of like the large scale learning that I was talking about, I would totally do that. There should be some state space that the model can use more effectively than what's available to it that we use as a rigid body like position velocity and stuff like that.
So a very related question is gain scheduling is very popular in aerial vehicles because as you change altitude, for example, your dynamics change, and certainly as you change speed, your dynamics change. So,
yes.
Somebody asked about the linear drag thing. How do you get more of these effects in some sort of gain schedule way?
Yeah, I think that's a really interesting question because you can say, okay, I'm going to use feedback linearization and then everything's linear, right? The gains don't matter, but actually they do because you run into things like constraints and things like that. So I think if you had no constraints, I would just say, just use feedback linearization. And then your gains, since your gains are applied in a linear space, it ends up working out in the nonlinear space. But because of things like constraints, and you might say, I want to be more conservative when I'm flying fast, which maybe from a control theory perspective doesn't quite make sense, but it makes sense from a human perspective. So I don't quite know what the best way to do that is. I mean, probably some sort of scheduling, right? Or some, like either you're going to hand design a scheduler of some sort, whether it's scheduling gains or some other feedback strategy, or you're going to optimize something in simulation that's given all of these things. What is the right way to, some sim to real type thing that optimizes the performance?
So in the world I live in, which is, humanoid control, and particularly legs, we originally started by trying to cancel the dynamics. And at this point, there's a strong consensus that was a really bad thing to do.
Oh.
And so I'm inherently prejudiced against feedback linearization. And I have some intuitive, non-formal notion that we should try to be as natural in our control as possible. So what does that mean? Change the dynamics of the plant as little as possible. Maybe that's what we get in optimal control when we put a huge penalty on effort or actuation. But here, you don't care. You're just, let's feedback linearize, let's drive the thing any which way, and it does what we want. Are you missing something by being so aggressive?
I think for the quadrotor, you can imagine, you can imagine some crazy stuff, right? Where like, it's okay to tumble because you're going in the right direction. So forget about control for a bit because it takes less effort. Stuff like that, it may be interesting. But for the more reasonable quadrotor flights, it seems to be less of an issue than in humanoids. But I think for humanoids, I can imagine the right way to do that would be to have some giant sim to real optimization where you like you said, you penalize effort, but you also make sure it does what you want it to do. And I think those things are very difficult to hand design or engineer.
So why aren't you doing what we're doing in the, I'm going to call it the big robot world?
I think for the Quadrotor, I think it's less of a detriment to cancel out these dynamics. Right. That's what I think. Especially, I mean, it's just like a drag that's slowing you down. So if you say I want to speed up, like there's no alternative. You can't use the drag. Although like if let's say the drag is hitting you and you want to slow down, you don't have to fight it, but that's going to happen automatically anyway.
So my final question is all of this totally esoteric, limited to Quadrotor stuff? How are you going to apply it? Should anyone else care?
Yeah, I think there are two parts to that. 2 points that I want to make. And the first is that people should look at the dynamics of their models, like the learned models. So a lot of people learn acceleration models and they don't look at the derivatives. And I think that can be useful in a model predictive control setting or even some inverse dynamics setting like I do here, where you can locally predict what's going to happen using the derivatives. That's one thing. Second thing, well, first, yes, I think this model learning approach can be used in other systems, of course. Just the way you use the model may be different depending on whether or not you can use differential flatness, but essentially you're doing some form of inverse dynamics. And second, I think the numerical optimization thing is pretty interesting. And of course, that's what people do. They learn a model and then they run MPC, which is effectively numerical optimization. But I think combining that with differential flatness and inverse dynamics is something people can do more of.
Okay, I think you did a great job. That's it for my questions. Nathan.
Thank you, Chris.
It's your ball.
Thank you, Chris. All right, I'll open it up one more time to the committee. Giuseppe.
So I have just 2 more questions. So the first one, when you did the outdoor experiments with the vision, so you were correcting the model based on the information that was given you by the vision sensor, or were you filtering everything? So how was that working?
Yes, the first one. So we're using the vision, completely the data from vision as it's coming in. And that brings up an interesting point is as opposed to feedback, which you have to do right now, with model learning, you can collect data and apply it later. Maybe let's say offline, but you can collect, say, a second of data, filter it non-causally, like apply some Savitsky-Golay filter, for example, and then feed that into the model. And that would get you a better output. And that's something you can't do with feedback. Like you can't take the state, filter it, and apply it later because it's already gone. But with model learning, you can do that. And I think if I had done that, it would have improved the quality of what the models are. That being said, for the vision experiment, I just used the raw data points as they come in one by one.
Oh yeah, I understand. But when there was the failure, was it already? Were you already correcting? Or
no?
Okay, so you were not. Let's say I thought that the failure could have been caused by a wrong learn part, caused by the vision sensor. That was I was thinking.
I think if I was learning, certainly it would have looked just. Essentially, the Z estimate of the camera just completely stayed still while the robot flew up. So it was completely a state estimation issue.
Okay, and then the other question is, do you think that, what kind of benefit would you get if you apply what you just learned, but instead of doing, let's say, all this feedback linearization, you apply more of a predictive control strategy? Can you do the same?
Yeah, I think so. So certainly in MPC, like you can query some model, right? MPC, like it depends on the type of MPC. If you're doing some, nonlinear optimization, certainly the better the model, the better that's going to be. Yeah, absolutely. I think so. And then if your MPC supports it, you should use the derivatives of that model as well. So that, yeah, I think that's something people do.
Okay, because maybe you can combine both. You can combine because you put them at the one, let's say at the two sides of the spectrum. Right. So what you can do is that you can learn in one way and then you use that in a predictive model to predict forward. But I was wondering why, if there was anything preventing that, but that's okay. You reply, you can do it. So.
Yeah, I also think maybe interesting to do it the efficient way first and use that as a hot start to the MPC. So it should be pretty close.
That's what I was thinking. Yeah. Okay. Okay, that's all. Great job. I mean,
No, thank you so much.
enjoyed.
Thank you.
Congratulations.
Thank you.
Great, thank you, Giuseppe. Chenglu, any further questions?
Yes, yeah, great answers. A lot of my questions got clarified. And one last question is, can you elaborate the basic assumptions between your approach? It seems to me that you need the state to noise mapping to be static. If it's non-static, for example, the wind is going in all directions, then this method, will it fail?
So yeah, as implemented and as I presented it, the assumption is that all of these errors are repeatable. So if you have a disturbance or a noise that, you know, yeah, is stochastic and time varying, I wouldn't say it fails. It does invalidate the assumption, but because we're getting so many data points in practice, and like we saw, we ran it in the wind when the wind gusts were coming. In practice, those data points get drowned out because there are so many other data points. Effectively, the average is really the true thing. But yeah, it's certainly something an issue. Like I think with GPS, it's probably worse because with GPS you get less data points, so you get like 5 hertz. And so during that faster trajectory, you're really only getting like a handful, like 5-10 data points at the fastest speeds. And so if those, say 30% of those data points are with a wind gust, you're going to learn the wrong thing. So yeah, certainly an issue.
Great. Yeah, thank you so much.
Okay.
Great, thanks, Chenglu. And Chris, checking back with you one more time. Any further questions on your part? You're good to go. Let's open up to the audience one more time. Anyone in the audience have any question for Alex? Feel free to unmute or raise your hand if you wish. I'm not seeing anyone. All right, great. Well, let's clap one more time and thank Alex for his fine presentation. Great job and answering our many questions. We'll now go into a closed door session with just the committee.